Okay, welcome back Physics 30s to our next lesson in Chapter 7. This is 7.4, and today we're going to be looking at half-life. Alright, so in the previous lessons we've been talking about radioactive decay. We have a nucleus like this, and it's unstable, so it's going to give off some radiation. For example, let's say that this neutron turns into a proton, and it gives off a beta particle of an electron and an antineutrino. What we're going to be looking at in this lesson is how long does this take? It's an unstable nucleus, how long does it take to decay? And you might think that, well, if I have a rock of radioactive material, this is an unstable nucleus, so it's probably just going to decay pretty immediately and they're all going to turn into their daughter nucleus. But that's not what happens. If we have a sample of radioactive material, it is a huge range in how long it's going to take to decay. Some could be in the order of magnitude of minutes, while others are in the magnitude of billions of years. And it's not even a set rate, like all of it will just go at that certain time. If you measure, say, 1,000 years, maybe only half of them will have decayed into their daughter nuclei. And you think, okay, well maybe then the rest of them are just going to catch up and they're all going to go rather quickly. But this doesn't happen either. It seems that when there's less of the radioactive material, a lower mass, the rate of decay slows. So if this happened in 1,000 years, wait 1,000 years more, and even less of them are going to go in that next 1,000 years. 1,000 years more, and even less. This gives us a measurement of decay called half-life, and it's because the rate of nuclear decay is proportional to its mass. So when there's less radioactive material, it's going to decay slower. Mass decreases, the decay slows. What half-life is, it's a measure of how long it takes for half of the remaining radioactive nuclei to decay. So this is what it looks like. So I have this chart up here showing the amount of polonium compared to lead. So let's say that this sample is a piece of radioactive polonium and it's going to decay into lead, polonium-210 to lead-206. Now let's say that its half-life is every 140 years. So I have this chart up here showing how time is going to change and the percents of each of these elements. So off the start at 0 days, we will have 100% of the polonium that's indicated in black. Now after 140 days, half of this is going to decay into lead. Like this, we can see that half of it has now decayed, half is green, half is black. Now over the next 140 days, it's not the same amount that's going to decay. It's going to be half amount of that remaining. So after the next 140 days, we will get going to 25% of the polonium remaining and 75% lead. After the next 140 days, half of that again to 12.5, half again for the next 140 to get to 6.25%. So it just keeps taking half and half every single time. Why this is useful is it can help us to determine how old things are based on how much of that radioactive nucleus is still left. An example is carbon dating for fossils. This is an example of a trilobite, a type of species that was alive a long, long time ago. And one method that we can use, or one isotope we can look at, is carbon to figure out how old life is. So this is because life is going to have carbon-12, the normal isotope of carbon, but also some carbon-14. This shows it half and half. It's not those proportions, but a little bit of carbon-14 and lots of the carbon-12. Let's take a look at how this works. So in the atmosphere, there's a lot of carbon atoms from carbon dioxide, and the most common form of carbon is carbon-12, and this is a stable nucleus. However, once in a while, we're going to get some carbon-14. This actually doesn't come from a carbon-12 nucleus interacting with a neutron, it comes from nitrogen-14. Our atmosphere is about 78% nitrogen, and when this collides with a neutron, this knocks out a hydrogen nucleus or a proton. So it's kind of like the exchange of a neutron coming in and a proton coming out. So the overall nucleons will stay the same, but it drops to 6 protons, which makes it carbon-14. Now I've shown it here as being 1 out of 10 carbon atoms, so we're going to use the number 10%. Again, this is not accurate at all, it's much, much smaller, but we're just using that as a nice, easy number. So this carbon-14 is radioactive and it's going to break back down to nitrogen. But we're going to look at the proportions of carbon-14 to carbon-12. So we have all this in the atmosphere, and then based off of plants doing photosynthesis, they're going to take in this carbon. they're going to have the same ratio of carbon-14 to carbon-12 since they're taking it from the atmosphere. Then animals are going to eat the plants and they'll have the same amount. So now let's look at the trilobite here crawling across the ocean floor. And carbon-14 is going to become a part of him when he eats things that are made of carbon. So the carbon-14 becomes a part of his chemical makeup. Now it's going to be the same percent. If there's 10% in the atmosphere, there's going to be 10% in that animal or in any other plant or any other form of life that is currently living. But then the trilobite reaches the end of its life, it dies, and it gets buried under sediment. And we discover it a long time later as a fossil. Now we can analyze the fossil and say we look for the ratio of carbon-12 to carbon-14 and find that it's 5%. What this tells us is half of the carbon-14 nuclei have changed, they have decayed. So now our ratio of carbon-12 to carbon-14 is half. So if we know the half-life, the amount of time that it takes for half of it to decay, we could figure out how old this fossil is. And we know that the half-life for carbon-14 is about 5,730 years. So if we had a case like this, we could say that that fossil is 5,730 years old. Now what you'll notice with this method is that it's really dependent off of that initial 10%, comparing that 10% to the 5. This is going to become less accurate if we don't know the amount in the atmosphere, the amount that the trilobite started with. If the amount that it started with is different than the current atmosphere, our method will get inaccurate. This is pretty consistent over time, but things like volcanoes, asteroid hits, and the production of carbon dioxide through burning fossil fuels will change the ratio of carbon-12 to carbon-14. So it can become a little bit less accurate with the more change in CO2. The other thing is that this actually wouldn't work super well for a trilobite because it's only accurate to about 50,000 years. So that would be about 10 half-lives, around that range. And we're starting to get to such small percents of the carbon-14 remaining that it gets a little bit inaccurate. And the trilobite is thought to be millions of years old when it was found with these fossils. So we'll have to use some other isotopes or some other radioactive materials that have a much longer half-life. And then when we compare them, if we get similar results, then it means we're definitely more accurate. Okay, so that's what half-life is. Now let's get into calculating it. So the formula is N is equal to NO times a half to the N. There's a lot of N's going on here, so let's sort them out. The first one means the radioactive nuclei that is remaining, that we still have. The NO is the original amount of radioactive nuclei. Okay, so we're going to take the original amount times by a certain amount of half-lives. So it's half to the order of number of half-lives. Okay, so if you took your original amount, let's say, just for an easy number, you have 100 radioactive nuclei, times by a half to the 1 for one half-life, you'd get half of that, you get 50. If we want to times it by 2 half-lives, we times it by half, then half again. So half to the exponent of 2, half to the exponent of 2 half-lives. So relatively simple formula. Now questions may not give you the number of half-lives, so you just have to figure it out from this formula where you take the time divided by the time of a half-life. So if you have a half-life of 10 years and 40 years has elapsed, you go 40 years divided by 10, because 10 is a half-life, and you get, well, that was 4 half-lives, and that's what would go in for that exponent n. Now, a couple other things that are worth noting here is that 0.5 to the exponent n gives us our percent. That's the amount of percent remaining. So really, we're just determining the percent, then multiplying by the original. And lots of questions ask for the percent, so it's sometimes good to calculate that first, and then we'll be able to have that number in case it asks for percent. I'll show you that in an example. The other thing to note is that this n could work for multiple things. This could be calculating our original amount of atoms and our final amount of atoms, or radioactive atoms remaining. It could be talking about the original mass and the radioactive mass remaining, or it could be talking about the rate of decay. Remember that the rate of decay is slowing as it gets smaller and smaller mass. So the mass and rate of decay are proportional. So it could give you those numbers as well. It says its rate of decay is this certain amount, that goes at the start, and then what's it going to be after a certain amount of time? We would use the exact same formula. And this is measured in becquerels, which is decay per second, and it's with the symbol BQ. So if you see questions like that, that's what it's asking about. Use the same formula. Okay, so now let's try an example. It says the half-life of bismuth-210 is 5 days. If 18 grams of the sample is left for 14 days, how much will remain after these 14 days, and what is the percent remaining? So we start with our formula, and I'm going to plug in the numbers of 18 grams, my half, and then raised to 14 over 5. Remember, that's the time divided by the time of a half-life. Now I'm just going to plug in my numbers here. I'm going to calculate this part first, so I get the percent, and then multiply by my 18. So this percent here, 0.14, and that'd be 14%, times by 18, and I can answer 2.584. So I like doing that step first, so then I can answer kind of both of these, or that percent step involved there. So now I can say the answer is 2.6 grams, because we have 2 digits. And then for percent, I don't have to say, okay, 2.584 divided by 18. I already have that number from the calculation right there, so I can just write 14%. Okay, let's try another one. This one says that 48 grams of polonium-218 is secured in a container. 18.6 minutes later, there's only 0.75 grams remaining. What is the half-life of polonium-218? These are often considered to be harder questions because we're trying to solve for information in that exponent. So when I write this formula, I'm trying to figure out information about that n. Now the n is number of half-lives, so I'm just going to sub in here the time over the time of a half-life. Okay, you can use different letters for exponents there, but that's just what I put. The time that's elapsed, and the h is how long a half-life is. That's what I'm trying to solve for, the number to the exponent. So what you could use to solve this is you could use logarithms. Now you may have taken this in your math courses, however for Physics 30, logarithms is not required. So because of that, all of your questions are actually going to have an even number of half-lives, which is going to make this actually kind of easy to work through, just by showing how much it's going to decrease each time. So this is kind of an easier way to solve it. You could say initially I have 48 grams. After one half-life, it's going to be 24. After another 12, I'm just going to keep dividing by 2. 6, 3, 1.5, and then get to 0.75. I said, okay, well, how many half-lives occurred there? To go from 48 to 24 is 1. So I'm going to put these arrows showing here all the different half-lives. We say that, well, it decreased by half 6 times. So now I know what that n value is. N is 6. There was 6 half-lives, and that's equal to the time divided by how long a half-life is. So I'll come over here now. N is equal to time over our half-life. So I'm going to plug in 6 half-lives, 18.6 minutes divided by the length of a half-life. Just rearrange that, and I should get an answer of 3.1 minutes. So that's how you can solve it without using any logs. Okay, so that's it for our lesson on half-lives. I hope that helped you to understand how they work and how to calculate them. Thank you so much for watching this video, and I will see you in the next lesson.